Hey everybody, we're going to be going over Newton's second law, and this is just the explanation video. So we're going to go over like what it is, what are the units, all the other stuff that you want to know about it, and then later videos we'll be getting into a bunch of examples using it. All right, so let's go ahead and get started. But first, let's do a quick revamp of what actually is Newton's first law. Okay, so Newton's first law, here's the slide we used to talk about it in class, but an object will continue its motion until a net force causes it to change. So anytime that we have a net force of something that is just not zero, a non-zero net force, that's going to make something's motion change. And by motion, remember, we're talking about velocity. So just that thought process of, okay, is my object accelerating? And if it is accelerating, then I go down this thought process. Yes, there has to be a net force because it's accelerating. And if it's not accelerating, then I know there's no net force. Or the fact that when I add all the forces, the net force is zero, right? So that is just kind of a thought process behind this. And we're going to use that later. That becomes a really important piece to setting up problems using Newton's second law. So. But moving on, long time ago, Newton, this good-looking fellow right there, came up with this rule of motion that talked about acceleration. And acceleration is proportional to the net force acting on an object, and acceleration is inversely proportional to mass. So if we write that out here with a little mathematical formula, put my little vector marks on there. Right? We know that's saying acceleration is proportional to net force. And for those of us that maybe don't recognize this little symbol right there, that is the Greek letter sigma. And that is the mathematical symbol for sum. So anytime you see that, basically we're adding all of the forces together. We're summing the forces, okay, the net force. And so, yeah, this is the technically like correct way to write it if we are talking about like how Newton really thought about how both of these things, mass and net force, affect the acceleration of an object. Okay. Now, almost all of you have probably seen Newton's second law at some point, and it's most likely been just the exact same formula, just reorganized a little bit to look like this. All right. And this is the net force on an object or a system of objects is equal to the mass times the acceleration. All right. This right here is Newton's second law. So questions that you kind of have to ask yourself whenever you're using Newton's second law and setting up how you're going to think about a problem when using it is, all right, what is going on for my object in the x direction, and what is going on for my object in the y direction? So for example, this one over here on the left that I'm going to take a look at. In the x direction, if I take a look at this, I can tell by these little motion marks, these little swoosh marks right here, right? They're getting further apart. I know this object is accelerating to the right. So when I start thinking about Newton's second law, let me get this right there, that would say, okay, in the x direction, I'm going to set up Newton's second law. So I would say the net force in the x direction is equal to the mass times the acceleration in the x direction, right? I know I can set up Newton's second law because it is accelerating in the x direction, right? Newton's first law tells us that. Now you're seeing why we tied in Newton's first law, right? Newton's first law tells us if there's an acceleration here to the right, then there needs to be a net force in that direction, okay? But now let's think about the y direction, okay? If this block is accelerating to the right, it's not just going down. You don't see somebody just kind of a car driving down the street and then all of a sudden it goes boom and just accelerates off towards the sky, right? So we know in the y direction for this block, there is no net force. So I know automatically what's going on in both directions here. I know that there is no net force in the y direction, and I know that there is a net force in the x direction. Okay? Same thing, this ball right here. So now we're looking at over on the right-hand side. This ball is accelerating downward, right? This would be an object that is in free fall. And so we can do the same thing. We approach it by saying, okay, what is happening in the x direction? Well, this ball is only accelerating in the y direction. So in the x direction, I know there is a net force of 0. It does not mean there's no forces. It just means that when we net the force, when we add everything up, they all cancel each other out and make 0. Okay, in the y direction, I would say that the mass of that ball times the acceleration in the y direction, right, is going to be equal to the net force right there. So I forgot my little vector marks on some of these forces, but all of those things right there, this is how we would set up and think about setting up Newton's second law for each direction. Remember, we treat x and y directions independently. Okay. So this is just like how we use Newton's second law to set up a problem. If we're going to look at the graphs, right? If we're thinking about graphically, what could this be? This is an equation, so obviously we have a math model to represent this. Well, if I graph Newton's second law and I have force on the y and acceleration on the x-axis right here. Okay, well, here's my equation for a line. And so think about it. If I say, all right, force equals whatever the slope is times the x-axis, which is acceleration, and then plus b, but b is 0, so we don't need to worry about it. Okay, so the y-axis, if you take a look at this, the y-axis here is net force. Good. Okay, we're good there. The x-axis is acceleration. We're good there. So what does the slope represent? That's what we're trying to figure out. And in this case, you notice this looks just like Newton's second law. So for this graph, the slope right here would be, whatever the value for that slope is, the slope would be the mass of the object. Okay? So that's how we can kind of start to think about our math models. If you ever have a graphical situation, just look at what does the math model look like, and then what equation does it actually look like that we can kind of refer it to. Okay. Cool. Just looking and thinking about units. So we haven't talked about the units we will use to represent this. So this is Newton's second law, right? And if we just think about what the units are, anytime you are talking about a force, that's going to be equal to a kilogram here in terms of mass times the units for acceleration, which is meters per second squared. Okay, so anytime I want to talk about anything in force, people were having to say kilogram times meter per second squared. And what that does is that's saying a force is how much it takes to move 1 kilogram of mass and accelerate it at a rate of 1 meter per second squared. Okay, so I got a 1 kilogram block, and I'm going to accelerate it 1 meter per second every second. People got sick of always referring to it like this, so the shorthand way we have for force is we call this a Newton. Capital N for Newton. Okay, so 1 Newton is the amount of force it takes to move 1 kilogram of mass and accelerate it at a rate of 1 meter per second every second. So units of force are newtons. Cool. That's kind of like the whole overview of Newton's second law, and then I will have further videos. I'll even put the links down in the description if you want for the examples to being worked out with some of this stuff. So I will. If you want to take a look at those, you can go ahead and click. Otherwise, adios.